Welcome to this explainer. I think a lot of us hear the word chemistry and immediately picture dusty textbooks and sterile laboratories, right? Well, forget all that. Today we're going to look at chemistry for what it truly is, the invisible magic that shapes absolutely everything in our everyday lives. From the food on our plates to the very atoms in our bodies, we're constantly surrounded by these fascinating chemical reactions. Let's start with a kitchen struggle we all know way too well. You're just chopping an onion, minding your own business, and suddenly, bam, your eyes are stinging and the tears are just pouring down your face. We've all been there. But have you ever wondered why that actually happens? Well, believe it or not, you are experiencing a highly evolved form of botanical chemical warfare.
Okay, let's dive into this. So, to an onion, your chef's knife is literally no different than a hungry bug looking for a snack. When that blade slices through, it breaks the plant's cells open, and that kicks off a whole sequence of defensive reactions. Basically, enzymes mix with sulfur compounds to create this volatile gas called propanethiol oxide. When that defensive gas floats up and hits the moisture in your eyes, it actually reacts to form a super mild sulfuric acid. And naturally, your body goes, "Whoa, get this out of here," and triggers your tear glands to wash it away. But think about what happens when you toss those harsh raw onions into a hot frying pan. The chemistry completely flips. The heat actually destroys the exact enzymes needed to create that tear-inducing gas. Instead, the cooking process kicks off a totally new reaction, forming a compound called bispropenyl disulfide. And that is exactly what gives frying onions that incredible, sweet, savory smell that just fills up your whole kitchen. I mean, it's the exact same vegetable, but a completely different chemical reality. Section 1. Elements breaking the rules. So from the cutting board, let's zoom way out to the periodic table to check out some elements that just completely ignore the rules of physics and behave like absolute magic. Take a look at this temperature, 85.58 degrees Fahrenheit, or about 29.7 degrees Celsius. That is the surprisingly low melting point of a metal element called gallium. Since your normal human body temperature is way warmer than this, around 98.6 degrees, a solid piece of this metal will literally melt into a liquid puddle right in the warmth of your bare hand. It's a completely safe, non-toxic liquid metal you can just hold. Actually, gallium's weird properties made it the star of a pretty hilarious practical joke. Back in the 1800s, these cheeky chemists used to cast ordinary-looking spoons out of solid gallium. They'd invite people over, serve them hot tea, and hand them these special spoons. As soon as the guest went to stir their hot tea, poof, the spoon would completely vanish, melting seamlessly right into the liquid. Imagine the looks on their faces. And gallium definitely isn't the only rule breaker here. Get a load of this rapid-fire list of chemical oddities. Out of the 118 known elements, bromine and mercury are the only two that are liquid at room temperature. Also, if you look closely at metals, gold and copper are the only two on the entire periodic table that aren't some shade of silver. Then you've got osmium, which reigns as the absolute densest stable element on our planet. And hey, let's not forget water. It's an everyday substance that bizarrely expands when it freezes into ice, while almost every other substance in the universe shrinks. And this brilliantly illustrates one of the most mind-bending concepts in all of chemistry: how just changing the arrangement of atoms changes literally everything. Take a diamond, the hardest natural substance known to humanity. Now compare it to graphite, that super soft stuff we use as lead in our pencils. Despite looking and feeling like complete opposites, they are both 100% pure carbon. The only difference is the geometric way those carbon atoms are bonded together. Wild, right? Section 2. The secrets of dry ice. Let's keep exploring materials that mess with our expectations. We're going to put a dedicated spotlight on dry ice, where extreme temperatures and pressures just completely warp the normal rules of matter. Now, what's really interesting here is the massive difference between the regular ice cubes in your freezer and dry ice. Standard ice, as we all know, is less dense than liquid water, which is why it floats in your cup. And when it warms up, it melts into a liquid puddle. But dry ice, which is actually solid carbon dioxide, is denser than water. That means it will sink like a stone if you drop it in a pool. But the craziest part, it doesn't melt. Yeah, instead of melting, dry ice undergoes this fascinating process called sublimation. Basically, sublimation is the transition of a substance directly from a solid state straight into a gas, completely skipping the liquid phase in between. That's exactly why we call it dry ice. There's literally no liquid mess left behind. Actually, to force solid carbon dioxide to melt into a liquid, you'd have to subject it to extreme pressure, like over 5 times the normal atmospheric pressure of Earth. The other defining feature of dry ice is its brutal temperature. We are talking a frostbite-inducing negative 109.2 degrees Fahrenheit. Oh, and here's a fun fact about that spooky, thick fog that billows off dry ice. That fog isn't actually carbon dioxide gas. Carbon dioxide vapor is completely invisible. What you're actually seeing is the freezing cold gas rapidly condensing the normal everyday water vapor in the surrounding air into an actual literal cloud of water fog. Section 3. Hands-on chemistry at home. So learning about extreme temperatures and rare elements is awesome, but you don't need a high-tech lab coat or liquid nitrogen to be a chemist. You can spark incredible reactions right in your own home. Seriously, just look at the magic sitting in your pantry. If you drop a standard egg into vinegar, a chemical reaction will dissolve the calcium carbonate shell, and you're left with a rubbery, bouncy egg. You can write invisible secret messages using lemon juice, and then reveal them by holding the paper near a heat source. You can use vinegar, salt, and a small electrical current to magically copperplate a standard quarter using electrolysis. You can mix up contact lens solution to create long, stretchy, ooey-gooey polymer chains we call slime. Or you can even build your own stunning, crystalline snowflakes using borax. And hey, after you're done playing with that sticky slime, even washing up is an act of chemistry. Getting your hands clean relies on a reaction called saponification. This is basically the chemical process that happens when fats or oils are mixed with a strong base, resulting in the soap that breaks down the stubborn grime and oils on your skin. Every single time you lather up at the sink, you're commanding a chemical reaction. Section 4. From stardust to your body. Okay, let's slow things down for just a second. We've talked about the kitchen, the lab, and household experiments. Now I want to zoom all the way out, way past our planet to connect your very existence to the cosmos. Let's start with a massive number, 900. If we were to break down the chemistry of your body, you contain an astonishing amount of raw materials. To put it in perspective, an average human body contains enough pure carbon to manufacture 900 standard graphite pencils. 900. Let's move to and see how this builds with another surprising number. Your body heavily relies on electrolytes to conduct electrical signals in your brain and your muscles, right? Well, to facilitate this, a healthy adult body contains roughly 250 grams of salt. You are literally a walking, talking chemical compound. So the crucial point is this. Where did all of those elements inside of you actually come from? The carbon for your 900 pencils, the nitrogen in your DNA, the oxygen you're breathing right now. None of it was created here on Earth. Every single atom of these heavy elements was forged in the unimaginably intense heat and pressure of nuclear fusion, deep inside ancient dying stars. And when those stars eventually exploded as supernovas, they scattered these essential building blocks across the void of space. Just think about that awe-inspiring reality for a moment. Those atoms drifted through the universe for billions of years, eventually coalescing to form our solar system, our planet, and ultimately, you. You are quite literally made of stardust. Which brings us to our final thought for this explainer. Chemistry isn't just something that happens in a beaker. It is the fundamental story of who and what we are. So I leave you with this. If you are literally made of the exact same stardust that powers the cosmos, what amazing reaction will you spark next? Thanks so much for joining me on this journey, and keep exploring the magic all around you.